I expect everything I'm going to say has already been said, but and probably better, but I'm part of the wind-up act. So, and I changed my talk at the last minute, which is always a catastrophic and stupid thing to do. So I was going to talk just about killer T cells, which I'm sure you would find infinitely fascinating, as I do, but I'm going to speak a bit more broadly. My background, I'm a biomedical scientist, that's what I'm known for, and but my background is I started in veterinary science, and I've sort of always been interested in the question of how we feed people and the public health aspects, and of course the One Health aspect that's dominating a lot of our thinking. And so I'll touch on some of that. I've only got 25 minutes, so I'll talk really fast, and you won't notice how contentless it is. So thank you. And the Sustainable Development Goals, we all should think in those terms, and of course you of all people do think in those terms constantly. And how we achieve these, I guess they're aspirations, really, aren't they? They're like the 10 suggestions that were handed down from God. And infection is my game. I've always worked on infection and immunity. And as we know, we're constantly challenged by new infections that come out of nature, many of which come out of our domestic animal populations, or they come out of wildlife populations. That is, we put more and more pressure on natural habitats, we get more and more these things coming out. Also, we can never quite predict what they're going to do. There are viruses that have been around in humans for quite a long time, like, for instance, chikungunya virus, that suddenly start to move, and they move up into Italy, out of Africa, and they move across the Pacific, across the Indian Ocean, rather. It's not into Australia yet. Then we've got Zika virus, which was hanging around in the Pacific for years, started in Africa. Suddenly we get it into South America. We get an enormous fright because it's causing these birth defects and so forth, and barely aware of it. So the immune system that we have, of course, has to deal with all these things, and they're constantly coming at us. And of course, the latest series that have been of interest over the last 15 or 20 years are the bat-borne infections like Hendra virus, and now we know, of course, that Ebola is a bat-borne virus, and SARS virus, of course, first brought them really to our attention. So many of these pathogens, some of them we have vaccines for, some we don't. Some we can make vaccines for, some there's various reasons why we wouldn't. Now, what allows us to deal with these, or all complex vertebrates to deal with these things, is the immune system. The word immune comes from immunus, which means without tax. And it defines soldiers in the Roman state who, after they came back from the wars, were, like international corporations and rich people today, exempt from tax. And they were called the genio immunium. So what the immune system is about is defeating the tax of infection, because microorganisms, viruses are very, very simple life forms, multiply very rapidly, change very rapidly, and of course we're slow reproducing, very long-lived, complex organisms. So we have this very complex immune system and very elegant immune system to actually deal with them. It's not perfect, it goes wrong, we get autoimmunity and all sorts of things, but it does a pretty marvelous job on the whole. And of course, we can help it with vaccines. The immune system divides into two bits. There's the innate immune system, which is kind of the immediate response system that's in all species, pretty much, right down to single-cell amoebas. And we share some of the immune mechanisms, for instance, that you'll find in fruit fly. In fact, some of the receptors that are important in our cellular immune system were found first in the fruit fly. So it's very broad through evolution. Immediate response, it pumps out a whole lot of toxic stuff to zap the incoming bug or whatever it is. Now that, of course, can have a downside too, because we can get so much of this stuff produced that we can actually damage ourselves. And we worry, for instance, about very pathogenic influenza viruses, which will trigger this innate system, this earlier response system. All this cytotoxic or toxic stuff comes out, causes vascular leakage. We can die in our own lung fluids. That's why, for example, with influenza, we quite not infrequently get unexpectedly high death levels in very, very fit young adults. So when the people who don't believe in vaccines or say, I know the immune system, all I have to do is take vitamin X or something, talk to you, tell them they're full of shit, and basically just being healthy won't protect you at all, it may actually kill you. more diplomatically than that. One has to be nice. And so all of the immune system is basically cell-mediated. These are the white blood cells. White blood cells first discovered back in about 1840, and the cellular the cell system is what secretes all these products, makes all these things, and makes the antibody molecules that, of course, are the protection that we generate by vaccination. Antibodies are secreted products. They're produced by the B cells, plasma cells. That immunological memory in that antibody system can last for pretty much a human lifetime, though we do like to boost vaccines every now and again to increase the numbers of these cells. And they're the molecules that are floating around in blood and protect us from a lot of infections. All the vaccines we have at the moment are pretty much antibody-based. The antibody to poliovirus, for instance, poliovirus grows in the gut. It doesn't worry us if it does that, gets into the blood, and where it causes damage is where it gets across into the brain. And so if you've got antibodies in the blood, they will take out the virus, it won't get across into the brain, and we're essentially protected. Now, many of our new drugs, if you'd asked, in my field of immunology, if you'd asked what are the important drugs that have come out of immunology with the money that's been spent out over the years, if you'd asked that 25 years ago, we'd say pretty much nothing, except some of the immunosuppressive drugs. But now we've got all these fantastic monoclonal antibodies that are made from our own immune response, essentially, which will block various things in that innate immune response or in other parts of the immune response, and will actually prevent particularly autoimmune diseases. They're knocking off some forms of cancer, and this is a big development. It's one of the reasons medicine has become so expensive, because these monoclonal antibody drugs are proteins. You have to make them under GMP conditions, good manufacturing practice, and of course, apart from patent coverage and all the rest of it, that makes them very expensive drugs to administer. It would be better if we could get away from them and get to small molecules, chemicals, but that's not an easy task. And they have made an enormous improvement in, for instance, rheumatoid arthritis, in multiple sclerosis, where you can now treat with these drugs and get much better life outcomes. Medical science has been sort of gradually, slowly progressing along, fairly quietly on the whole, but our treatment options now are infinitely better than they were 15 or 20 years ago for many cancers, many autoimmune diseases. There are still some cancers we haven't got anywhere with, like pancreatic cancer, but we'll get breakthroughs, I expect, and we'll move on. Now, as I said, the vaccines that we have are all pretty much based on antibodies. They work pretty well against what we call systemic infections, that is, infections that get disseminated around the body in the blood, like measles or polio. And they work pretty well against viruses or bugs that don't really change in us or haven't worked out some way to hide. We still don't have a decent vaccine for tuberculosis. After so many years, we don't have a vaccine. We worry very much about drug-resistant tuberculosis. It's not going to wipe out the human race, but it's really dangerous. It's very prevalent in South Africa, where we have lots of immunosuppressed people with AIDS. And it would be great if we could actually get a vaccine against it. And the fact that there's so few drugs in the pipeline that can actually stop it is really concerning. People like the Gates Foundation have stepped in, providing funding to try and get better drugs. Tuberculosis won't wipe out the human species. Even before we didn't know what it was and how it was caused and all the rest of it, it kills some people and not others. I don't think there's any infection out there that's likely to wipe us out. I have this speculation that it's a favourite fantasy on the part of, say, extremely rich people who are climate change deniers, that we don't have to worry about global overpopulation or something, because God will send a nasty bug that'll kill out all these unnecessary people and we'll be in good shape, and it won't affect us. The realisation that's sometimes not true, for instance, that influenza kills everybody, was one of the reasons George W. Bush put money into it. But he suddenly realised even rich people die of flu. But I don't think, as we face the problems of our species, I don't think we can rely on some sort of external agency to solve them for us, whether it be an infectious disease pandemic or anything else. We have to use rational approaches and sound policy. And of course, as you know, sound policy in many areas is substantially lacking around the planet. And I guess that's your area. But again, another problem we have with vaccines, apart from the fact we haven't been able to make a vaccine against the AIDS virus, and we have trouble with influenza because it changes all the time. We have to make a new vaccine every year, not a particularly good vaccine, it turns out. The other problem is, of course, that we have the resistance to vaccination, particularly in well-to-do communities. And that's kind of sad because we are getting regular outbreaks, for instance, of measles in this country. People seem to think measles is a harmless sort of virus. It's a far from harmless virus. It goes around the body and the blood, it gets into the brain, it can get into the ears. When we had measles active, you get 1 in 1,000, 1 in 2,000 kids dying of encephalitis. You get deafness problems, you get long-term lung problems, you get all sorts of things from measles, and it's not an infection that anyone should want to have. And so that is the problem, one of the problems with vaccination. The other problem is affordability. We've had a very good vaccine for yellow fever for years, but it's reasonably expensive. And so it's not given everywhere, and it's not necessarily given in places where it's needed. And then there's the other question of economics. Is it economic to make a vaccine? Maybe it is economic to make a vaccine against Zika virus, or maybe there are good social reasons for making a vaccine against Zika. But we haven't, for instance, made a vaccine against West Nile virus, which came into the United States some years back. It's killed a reasonable number of people from encephalitis, but obviously the cost-benefit equation has not led to the point where we've actually had a vaccine made and available to the public, though it is available for horses, which are much more valuable than human beings. And influenza, if we're thinking about pandemic infections, influenza is our main threat because the virus changes all the time and because it comes out of nature. We can't predict what will happen. The one pandemic we've had this century, the swine flu pandemic, was basically, it was 2 pig viruses that infect pigs but weren't coming across into humans. They reassorted, the genome has 8 different bits. They reassorted to make a new virus, which became incredibly infectious for us, went around the world very, very quickly. Not too terrible, though much more terrible in developing and poor countries and indigenous populations than it was in well-fed Western populations. And so a virus that only affected pigs suddenly changes to become a virus that infects human beings. And this is the danger with influenza. We get something totally new out of nowhere that we didn't really expect to happen. Very infectious, though you're pretty all right on a plane on the whole, unless you're sitting within 2 or 3 seats of someone that's got one of these things. It doesn't go around through the air handling systems. Now, what I work on is what's called the killer T cell of the immune system. This is like in the immune Roman analogy, it's like the Roman legionnaire who gets up close and personal. You know, Roman legionnaires fought with a big shield and a little stabbing sword, and they sort of bumped the person in front of them and stabbed to the right and just stuck them in the tummy. And basically they had to pretty much make contact. And that's what this cell that I work on is about, and you can see it working in the next thing. If you watch that green thing is a killer T cell. It's going to kill that cell. It's groping all over it. This is over a time lapse. And now you can see it's broken the membrane, it's leaky, and now that cell's killed. That's pretty dead. And so that's a killer T cell. These movies were made by Misty, who was one of our graduate students. And what the killer T cell is recognizing is a bit of a pathogen that's expressed in our transplantation molecules. I don't really have time to talk about that. That's why we got the Nobel Prize, though, for making some good guesses way back about that and making a discovery. And then lots of other people worked on it, and we got the Nobel Prize, which is a really good deal. And so I wrote a book called The Beginner's Guide to Winning the Nobel Prize. One of the useful suggestions in there is discover something really big. You know, how useful is that? I mean, get lucky. I mean, Though I must say, someone made the observation, the harder you work, the luckier you get. Not necessarily true, you need to think as well. Anyway, it's been worked out, and it's now the basis of, we think we may be able to use this aspect of the immune response, perhaps to develop better vaccines. These are the cells that are being mobilized in the new cancer treatments. If you've heard about, for instance, Jimmy Carter being saved from melanoma, or local businessman Ron Walker being saved from melanoma, this is basically due to the fact that we knew that a lot of these cancers had these killer cells sitting in them. but they weren't doing anything. Various people tried to wake them up. They took the tumours out, got the cells out, stimulated them in culture system, injected them back in. Results were very unpredictable. And then a guy called Jim Allison discovered that they're actually switched off through a particular switch mechanism on the cell surface called immune checkpoint. And they made monoclonal antibodies against these immune checkpoint inhibitors. And that's what's curing people from about 20% of people who would have died from melanoma. Now, there's still 80% who are dying, but we're curing 20% who would have died. And that's pretty substantial in cancer therapy. What we're doing is giving an antibody treatment, waking up the cells within the tumor itself, that then destroy the cancer, and then move out and find any metastasis, that any of the cancer that's disseminated, and destroy that as well. So it's a fantastic way of therapy, and we need to enhance it. We're also working on other approaches, or various people are working on other approaches to engineer cells using genetic engineering techniques so that they'll do this and take out various types of cancers. At the moment, it's only working well for some of the blood cancers, because the cells don't seem to be going into the tumours. Lots we need to understand about this, about how cells move, how they migrate, how they invade, and how they get their signals, which of course are all sort of chemical signals on gradients. Now, memory, immunological memory, I talked about it for antibodies that last 50 years, also for these CD8 cells, and we can induce immunological memory to viruses. Specificities are a bit different, and that may have a role in vaccination, especially against viruses that change very rapidly. It's not going to solve the AIDS problem. So there I'm going to kind of leave immunology and just talk about the general challenges that are facing us. And I'm sure you've heard a lot about this through the meeting, and I can only cover a bit of it. But as we all know, there's about 1 billion people in the world who simply don't get enough to eat each day. On the other hand, we have a global obesity pandemic. A lot of that obesity pandemic, say if you live in the American South, where I've spent a lot of time, is due to the fact that takeout food, the McDonald's type thing, it's simply cheaper and easier to eat that. And especially if you don't have a functioning kitchen in your house, you can actually feed and get a lot of calories like that very quickly. And of course, we have this great obesity problem and the concurrent diabetes problem. And then some populations are, of course, genetically set up to be what in the veterinary world we would call efficient converters. And they simply lay down too much fat when they're fed more than adequate calories, and then we have diabetes and all the problems that go with it. So that's a major problem. Then we have micronutrient deficiencies. We could correct some of those possibly by using genetically modified plants, for instance, in the food supply. And we all know probably, I would expect, about the saffron rice, but that hasn't really caught on. It hasn't gained wide acceptance. There's been a substantial campaign against it by some of the environmentally conscious organisations, and I think a lot more people are dying than need to if we could apply some of these technologies. And I think, quite frankly, as we face the challenge of feeding the world with increased stress on water and food supplies, we're going to have to take every option that's available to us. And I'm not suggesting GM's the only option, but I'd say it's one option, and it's one option that allows us to make, say, drought-resistant organisms reasonably quickly. So we have to take advantage of whatever science can offer us and whatever engineering can offer us, while at the same time ensuring that we're safe. Agriculture is challenged by the fact that the Green Revolution was fantastic, and Norman Borlaug got a Nobel Prize for it and so forth. But in the process, the Club of Rome that sort of postulated way back that we would have a problem with food production was always discredited, because we've done perfectly well at feeding the majority of people, if not all the people. But in the process, we've drained the aquifers. Aquifers have become contaminated with things like arsenic in India and Bangladesh and elsewhere. And of course, there's also the problem of saltation of aquifers, as in areas like Bangladesh, you're getting more and more seawater incursions. So there's real problems with water, and the real stress points in the longer term are going to be over, one suspects, over food and water. Human numbers increased fourfold at least through the 20th century. I graduated from the university. I've just been at the 55th reunion of my graduating class. All these old people came, and strange. And basically, the world population has more than doubled since we graduated from university. And that's created great stresses as well. Some of that has been due to the medical sciences, which have made vaccines and so forth. But we still have this issue of getting good health care, especially to women and children. And of course, regressive moves on the part of so-called conservatives are cutting back that funding for women's health, which is both a national and international catastrophe, and I think actually a crime against humanity, quite frankly. I looked at the crime against humanity statutes with respect to the Second World War. They were drafted in retrospect to nail these criminals who'd done these terrible things. It's a pity we can't get that sort of body of law out there as a suggestion and a preventive rather than as a retrospective act. Because with things like climate change and things like women's health and so forth, we need to act now, and we need to act preventatively. And acting retrospectively, many of these things will be far too late. We need hugely increased amounts of cereals. I started out in veterinary science because I thought I wanted to help feed the world. I was an altruistic kid and thought that was the problem, and I've been influenced, obviously, by the Club of Rome pronouncements. If I was going to go in that direction now, I'd go towards the plant sciences, because we all understand how much water and so forth the animal sciences use. But on the other hand, if you go to Africa and developing countries, animal agriculture is still enormously important in many, many respects. And there are many areas that can't really be accessed for food production except via animal agriculture. So animal agriculture, as you know, in developing countries, it's not only about producing meat, it's about producing milk, it's about traction, it's about producing manure, which is important. You know, the green guys who all want to save the planet by natural means all want to put manure on their plants, so that's also important. Health. The health community is becoming increasingly conscious of the threat posed by anthropogenic climate change. The oldest medical journal in the world, I think it's the oldest, The Lancet, has this commission which will report every 2 years, I think till 2030. It's basically Europeans and Chinese who are getting together to assess health risks through climate change. As you know, there are so many aspects to that, from contaminated water through flooding, through the movement of insect-borne diseases away from the equator, and various other aspects of it. I keep arguing that we need to think of planetary health in the same way we need to think of human health. We need to think of duty of care. A doctor has a duty of care. People who are political leaders have duty of care, and they're abrogating that duty of care for short-term goals, and we have to, in somehow, influence them to change. And it's disastrous if the only way we can get people to change is for a catastrophe to happen. But unfortunately, that seems to be part of the human condition. So we need massive change. We need to react to the global carbon challenge. We need a green economy. And if that's where the odd thing is, that's where the opportunities lie. That's where the opportunities for development, for innovation, for new technology lie. But unfortunately, the people who, for instance, control fossil fuel industries have vast amounts of money and a lot of political clout. And they're actually, I think it's not that we're anti-industry, we're anti-new, innovative industry, and we favour old, dirty and disgusting industry, and some pretty appalling people in the process. So we're at a defining moment in history, I think, and we're not really reacting to the challenge in the way that we need to. We will, but the longer we leave it, the harder it will be. And then there's the challenge of disinformation and the distrust of personal expertise. Now, I wrote this before the election of Mr. Trump and all the fake news that came out of various places. And I think someone described Fox News as faux news. But that's one of the problems. I sometimes think that Joseph Goebbels, Hitler's information minister, is the father of modern advertising, but that's probably not very nice to some of them. Some of them are better than that. And so that's where I'll leave it. Thank you very much. 25 minutes, I'm done. Okay.